Okay, so so what we've seen so far is some modeling, stochastic modeling of from a fairly abstract point of view, and Max has given a nice overview of deterministic modeling and also looking at some particular settings. So the idea of this last part was a little bit to look at, I guess you can call them fairly toy examples, but the idea is to understand a little bit how globally these methods can be applied, and particularly the interactions between what you can say with stochastic models and what you can say with deterministic models. So the starting point is really a very simple setup, but it was motivated by quite a nice experiment which was done by Saitaru and his collaborators in a paper from 2007. So what they did is they built a microfluidic chip, which is, so it's just a channel of around 400 micrometers, and it has a width of roughly 100 micrometers. And what they did is they introduced a bunch of polystyrene beads into this, and the idea was just to verify Fick's law. So to look at what is the flux distribution and so on. So what I want to do in this first part of this talk is really sort of follow along the lines of this thought, and to try and think a little bit about what is the impact of the number of molecules in the system, and when is it interesting to use stochastic models, and when is it interesting to use deterministic models. So in order to do this, what we've seen from Max's talk in his microfluidics example, so we typically have two extreme modes of operations of these systems. So one is pressure-driven laminar flow, where basically it's a completely deterministic system. Your beads, if you like, are sitting in this moving fluid, and they'll go at the velocity that this fluid goes at. The other case, we have diffusion. So in this is the case where we wouldn't expect to have any flow at all. And so if we have a small number of molecules, then we would expect potentially to have some stochasticity. So if we wanted to try and model it, well, of course we ignore some features which may be important in a more general microfluidic model, but what we can start with is a Smoluchowski equation from the beginning, right? So what we have is this term here, which is going to correspond to the external force, which is generating this pressure-driven flow in this microfluidic channel. And we have over this side the random perturbations, which are going to model the interactions between the molecules of interest in the system and the molecules comprising the fluid. So if we're interested in laminar flow, then this is the case with low Reynolds number, and so this term here is effectively corresponding to the drift velocity of the fluid in the channel. Okay, so if we want to think about trying to some extreme scenarios, when are we interested in applying deterministic models, and when are we interested in stochastic models? Well, if we go back to the Langevin model, well, what we may expect is, well, this term is deterministic, and this term has some uncertainty to it, so we may expect that if this term is much bigger in some sense than this term, then probably we should model it deterministically, and if it's the other case, then maybe a stochastic model is more interesting. So we can do this, and if we ignore the random perturbations, which are the interactions between these molecules and the fluid, then we just get an ordinary differential equation of this form, right? Which is a deterministic model. So that's fine, but what we haven't said anything about is what actually this value should be and this drag coefficient should be in a realistic system, right? So what is known, in fact, is that what we can expect is that as time goes on, if this system is like there's no changes to the environment, then what it will do is it'll equilibrate, right? And so what this means essentially is that the flux due to the drift and the flux due to the random perturbations, they should cancel out. And this general phenomena, which is known as a fluctuation dissipation theorem, allows us to relate the drift component, the drag component, and the variance component of the diffusion. And in particular, if you match it to what you would expect from essentially the Boltzmann distribution, which we would expect for a system in equilibrium to have, then you get a relation like this. So in the case you're interested in where you have drift, then this is known as a Stokes-Einstein relation. And so this gamma here will come from the Stokes formula. So in general, what we can see is that if this external force, which is generating this pressure-driven force, which is generating this flow, is much bigger than the Boltzmann constant multiplied by the temperature, then we may think that it's interesting to do a deterministic approximation. Another way of saying this is just that the drift velocity is larger than the diffusion coefficient. Okay, so at the other, I can go back to where I was. So at the other extreme, we just have a pure diffusion model. So this is just corresponding to a stochastic differential equation corresponding to Brownian motion, right, without any drift. So what we can ask then in this case, so we've seen that if there's no random perturbation, a deterministic model is interesting. But if we have this random perturbation, under what situations is it still interesting to model this just by purely a diffusion equation or the heat equation, right? So we got some insight into this from part one, briefly at the end of the Langevin diffusion section. So what we know is that if we have this kind of dynamics, then its evolution is described by this Fokker-Planck equation, right? Which is just the equivalent of what Max was showing before, except instead of the concentration here, we have this probability density of the location of the particle at a particular time. So we can see that there's a very close relation to Fick's law, just if we replace P by C in this setting. Okay, so what we can ask first is that if we have n molecules in a fixed volume, omega, then we're interested in the number of molecules that are in a particular region of this channel, right? So we can ask the question, well, if we increase the number of molecules, what is going to happen? So we saw before that this quantity can be approximated by a particular Gaussian distribution in the case where the probability of being in this volume is sufficiently small for a particular molecule. But this mu parameter, this parameter of the mean and the variance of this Gaussian model, it depends linearly on n. So in fact, if you fix the volume and you increase the number of molecules you put into the system, and you're interested in the quantity of molecules in a particular region, then you end up with this kind of behavior. So as you're increasing the number of molecules, your variance is increasing as well, right? So what this is suggesting in some sense is you're increasing the number of molecules of the system, and the uncertainty about the number of molecules in a particular region is actually increasing. So this is maybe a little bit counterintuitive from the usual perspective where you say, if I increase the number of molecules in the system, then it becomes less random. But in this particular instance, you increase the variance, which is in some sense increasing the certainty. So where does this link between the deterministic modeling and the stochastic modeling actually arise? Because it's not here. So what we can do instead now is we consider a one-dimensional system, just to simplify our life a little bit. We're going to have n molecules in it. They're going to evolve independently. And we're going to have a region which they're going to live, which is going to depend on the number of molecules in the system. So as the number of molecules increases, the length of our microfluidic channel, if you like, is also going to be increasing. What we're also going to have is some reflected boundaries on the end. So this would probably correspond better to a semi-realistic model of a microfluidic channel. The evolution of molecules in the system is going to be governed by this Fokker-Planck equation, where the diffusion coefficient is also going to scale with the number of molecules n. Okay? So what we're doing here is that we're increasing the number of molecules, and at the same time increasing the length of the channel, and at the same time increasing the diffusion coefficient, so essentially they can move more easily throughout the channel. So what we said very quickly in part one is that if we look at this notion of concentration, so this is the proportion of molecules in a particular region, Vn, which is also going to scale with the number of molecules, and we normalize it by the number of molecules in our system. So we can think of this as some kind of concentration. then it will in fact converge to this quantity here, which is the probability of a molecule described by a particular system, which I'll detail more, being in a particular region, V1. And so this V1 is the case where n is 1 here. So what we're doing, in some sense, is approximating the behavior of a number of molecules in a very large system by the behavior of molecules in a much smaller one. But we're going from, this is a stochastic system over here, but in some sense this is a deterministic one over here. Okay, so the trick here though is that this p tilde here is not the Fokker-Planck equation for this system up here, which has a length of n and a diffusion coefficient of n. It's going to be this Fokker-Planck equation here, where we have a diffusion coefficient of 1 and a length of 1. Okay? So what we see, if we want to apply this argument here, if we're trying to link a stochastic model to a deterministic one, what we need in the stochastic model side is for the number of molecules to be large, the system size to scale with the number of molecules, and also the diffusion coefficient to scale with the number of molecules. And if you do that, then you can relate this concentration in this setting, so the number of molecules in a particular region, with the behavior of a much smaller macroscopic or deterministic system, right? So we can illustrate this a little bit in this figure here. So what these curves are corresponding to here are different n. So these are corresponding to, this n is corresponding to the number of molecules, but at the same time the size of the system and also the diffusion coefficient. So what we see is that when n is small, so we have this red curve. So this is the probability distribution for the number of molecules in a particular region, which is going to be n divided by 8, between n divided by 8 and n divided by 4 in this particular system. So what we see is that n is small, we have quite a large variance. So what that's telling us is that we have quite a lot of uncertainty in the number of molecules that are in this region, or the proportion of the number of molecules that are in this region. But as we increase the number of molecules, or the scale of the system, then we see that the variance reduces quite dramatically. And in fact, as we're increasing n appropriately, then we should converge to this macroscopic solution, which is governed by this solution of this diffusion equation with diffusion coefficient 1 in this system of length 1, right? So this has quite a few interesting consequences. So the first one is that if you have a very large system with a lot of molecules, then, and you're interested in the proportion of molecules in a particular region, then what you can do is you can try and approximate this proportion by the solution of a diffusion equation in a much smaller system. So that's the first point. The second point is if you have a very small, so if you have a deterministic model, so one of the ones Max showed, for example, and you're interested in, you don't feel like solving it for whatever reason by using numerical methods, such as finite element method or so on, then you can obtain a particle-based solution by considering a very large system with a large number of molecules and say large diffusion coefficient. And so, depending on what you want to do, this link between this macroscopic and this stochastic modeling can be useful, I guess. So I think I'll end there, and I hand it over to Sebastian to give the second example.
Thanks. Okay, so as we said, we have two application examples. This was the first one, and the second one that we have is some example which should go more into the direction of a actual molecular communication setting. So in this second application example that we want to discuss, we have a transmitter, a channel, and a receiver. So the transmitter in this example, it would be some sort of prokaryotic cell which can express some proteins, or which we consider as signaling molecules. So we consider the transmitter to express some signaling molecules over some time interval, and after this time interval, there would be some time tau b, at which the cell would open up its membrane basically to release the signaling particles. So from this time on, the signaling particles would diffuse in the environment until at some time they would randomly be observed by the receiver, which in this model would just be an absorbing boundary. Okay, so this is the system model, transmitter, bacteria transmitter, and then a diffusion channel and a receiver. So in the following slides, we want to basically discuss which parts of the system, or I mean basically which questions that we could possibly have regarding the system we could answer using the modeling techniques and the solution tools that we discussed in the first part. Okay, so this should somehow show you basically, or this should somehow show where to apply all these models that we discussed before, or at least part of them. Okay, good. So what could we possibly want to know about the system? So one very basic question could, for example, be, so this bacteria cell, the transmitter, it has some time to express signaling molecules, right? So one question could be, on average, how many signaling molecules are expressed by the bacteria cell, right? I mean, this could be a very basic question that we could ask. Then again, we could ask a similar question for the number of molecules counted by the receiver. So we could say, for example, given a certain number of signaling molecules released by the bacteria, what is the expected number of molecules observed after some time by the receiver, right? And then further questions we could ask would be, how do actually the system parameters, which we introduce in a bit, so for example, the size of the volume and so on, how would they influence these values, right? So how would the expected number of observed signaling molecules scale with the dimension of the system, scale with the diffusion coefficient, and so on, okay? So, yeah, and then other questions could also be like related to the stochasticity of the processes that we observe. So, is the stochasticity, the randomness basically in the signaling molecule expression the dominant source of randomness in our system, or is it a diffusion noise? So to which sources of randomness that we have in our system, which is reaction noise basically and diffusion noise, should we pay more attention, which is like in a sense more important for us to consider in detail to model, or are they, or on what does it depend basically, what is the dominant noise source? And then finally, one very specific question that we could ask in terms of system design is, if we have some symbol interval, so some finite time t, what is the time in this symbol interval that we should reserve for the bacteria to produce signaling molecules, and equivalently, what is the time that we should reserve for the signaling molecules to diffuse within the symbol interval towards the receiver, right? So, I mean, we could ask many design questions, but this could possibly be one of them. So basically, how to choose this this time instant tau b in some optimal way. Okay, so the time at which the bacteria basically starts to release the signaling molecules. Okay, so in the following, we basically start with simple models, and then we go on to more complicated one in order to show basically what insights they could possibly provide us. So first of all, for this, for the expression of the signaling molecules, we assume the following model. We have inside the bacteria, we have two reactions. One is a zero-order reaction in which signaling molecules are just produced out of nothing. Okay. And then the other reaction would be a first-order degradation reaction, where due to some processes, the signal molecules degrade to any species which is no longer observable by the receiver. Okay? So for this simplistic model of the signaling molecule expression, we could have a obviously a model in terms of the chemical master equation, which in which the probability to observe some number of molecules of some number of signaling molecules would depend on the expression rate for these molecules alpha and the degradation rate mu. Okay, so this is basically the model that we assume. And now, and it's of course a system of equation, right? So we have one equation for each number of signaling molecules in our system. So it's actually infinitely many differential equations. Okay, so now if we wanted, for example, to determine the average number of signaling molecules produced by the bacteria, what we could do, we could modify this equation a bit. So we could multiply both sides by E, and then we could sum up over the over E, and what we would obtain would be a so-called moment equation. Okay, so we would obtain one single differential equation, which would provide us with the time evolution of the expected number of signaling molecules over time, basically. Okay, so this is this very similar, very simple ordinary differential equation here, and we can solve this to obtain the number of the expected number of signaling molecules over time as an explicit function of t. Okay, so this is basically to show that. So this could, for example, be useful to determine the influence of the different system parameters, alpha and mu, that we have on the mean number of molecules over time, right? So we see that the ratio of alpha and mu determine more or less the amplitude or of the expected, or say the steady state value of the molecule concentration, while the mu determine the speed at which the molecule convergence would concentration would converge on average to this value. Okay. So this is the two observations that we can make from this first very simple model. Okay, so then basically the next question that we wanted to discuss is, given some number of molecules released into the environment, what would be the average number of molecules observed at the receiver, right? So for this kind of question, we have learned in part 2 that we should study the diffusion equation, or even in part 1 actually, because that would eventually give us the number of received molecules. So this is exactly what we do here. So we set up the diffusion equation for our reaction volume omega, which is just a box basically in our case. And then we choose the appropriate boundary conditions. So we have a reflecting boundary basically at the left-hand side of the box. And here is the reflecting boundary, and then absorbing boundary at the right-hand side of the box. Okay. And then we can actually solve this model because it's, it's fairly standard. So what we get is one of these series expansion that were introduced by Max before, which is here the sum over the cosines and the exponential function. So you may somehow recognize it from part 2 of this tutorial session. So the question then is that you could immediately ask, like when we were talking about analytical models, we were talking about gaining some insight on how the system parameters would actually impact the system, right? But this series expression is rather inaccessible in some sense. So what we could possibly use it for, we could use it to derive approximate expressions, right? So what I want to show on this slide is basically that even if we get a somehow complicated analytical expression, we could still, in some cases, get some insight by appropriate simplifications. Okay? This could be one of the take-home messages here. So if we look at this term here, so what we, okay, so first of all, perhaps, what we're interested in is the absorption time for any particle P, which diffuses in the box, right, up to time t. And this can be expressed just as an integral, basically, as a time, as the probability that the molecule would still be in the box at time t, which is this integral here, right? So this is sort of the accumulated probability mass of the particle location in the box at some time t. And then if we take 1 minus this probability, we obtain the probability that the particle is already absorbed, has already been absorbed by this time t, right? Okay, so if we plug in the series expansion here, and we have a closer look, we see that we basically have a sum of decaying exponentials here, right? So over time, what would happen is that each of those exponentials would go to 0, but they would go to 0 at different speeds. So the dominant term would be that exponential that would go to 0 with the lowest speed, right? So if we use this observation, we can actually derive a approximation for the absorption probability for the, of the particles in terms of the first term of the series here, right? And what we end up with is this expression here. So we obtain that the absorption probability is larger or equal than 1 minus 4 divided by p times exponential minus d p squared divided by 4a squared times t. And I'm spelling this out because I want to emphasize that in this expression we have basically all the system parameters present which characterize the diffusion environment and also the diffusion of the particle itself, right? So we have the diffusion coefficient here, we have the size of the box in x direction in the denominator here, the a here, and of course we have the time variable t here. Yeah. So basically the point I want to make here is that using this first order approximation of the very complicated expression, we can still get some insight on how the system parameters would eventually impact the behavior of our system, right? So as we increase the diffusion coefficient, for example, this term here will vanish more quickly. So we will, the particles will get absorbed more quickly in the end. Okay. Okay. So this was basically, yeah. So this was this, and then we can also see that actually the first time approximation that we just discussed is a useful approximation. Okay. So if we look at the average number of molecules absorbed by some time t, or equivalently the absorption probability, we see that the first term approximation, which you see in orange here, provides actually a good approximation to the true absorption probability, even for slow absorption probability numbers. Okay. So if we're interested mostly in this area here, we can make our lives a lot easier by just considering the first term. This is basically the message. Okay, and then of course we want to go a step further. So next thing we want to consider is actually the number of observed molecules or absorbed molecules equivalently is a random variable, right? So we want to ask, what statistics does this random variable actually have? And in the case of diffusing molecules that are assumed to diffuse independently, it's actually quite simple, because for each of those independent molecules, we at some time t we would observe a Bernoulli experiment, right? So either at some time t, either the particle is absorbed by the boundary, or it's not absorbed, right? So these are the two possibilities. So in the end, for the number of particles absorbed by some time t, we get a binomial distribution which has expected value equal to the number of released molecules times the absorption probability, and variance equal to this term here, basically. Okay, so now we basically have a simple statistical model for our received signal, so to say, under the assumption that we know how much molecules have been released. And to somehow see how useful this characterization is, we see in this plot here some trajectories of the system for different numbers of released molecules, and we actually get the same picture as MolCom already laid out in the first part of this third part of the tutorial. So if we release few molecules, so say 25 molecules are released by the bacteria cell, then we would observe a signal which is rather noisy compared to what we expect on average, right? On the other hand, if we would release more molecules, the received signal would be more centered roughly around the mean, right? And this is basically because the coefficient of variation, so standard deviation of the number of observed molecules relative to its mean, scales with the inverse of the square root of the number of released molecules. Okay, so the more molecules we release, the less will be the relative deviation from the mean. So this is basically what we were discussing before. Okay. Okay, so then basically what we assumed so far is that we have a deterministic number of released molecules. But what if we're dealing with low copy numbers in the bacteria cell, right? So what if the chemical reaction network in our bacteria cell is a highly random process? Then we actually need the full statistics of this process in order to get the mean value of our observed signal even. So what we could do, we could consider our chemical reaction network as some sort of birth-death process, right? Which has this form here, and the states of this birth-death process would correspond to the number of signaling molecules produced by the bacteria cell. Okay. So the first simplification that we now make in order to proceed is that we observe this birth-death process in equilibrium. Okay, so we give the bacteria infinite time to produce signaling molecules. So in that case, what we can directly derive from this representation here is actually the complete probability distribution of the number of observed molecules, because in this birth-death, just let me go back for a second. In this,
yeah,
You're back.
You're back.
You're back.
thanks. Yeah. So in this birth-death system in equilibrium or in steady state, say, we'll always have the condition fulfilled that this kind of transitions here are as frequent as this kind of transitions here, right? So if we use this condition, we can set up a system of equations here, and then if we, in addition, apply the condition that we should get a probability distribution, we get to the conclusion that the number of particles produced by this chemical reaction network actually follows a Poisson distribution, okay? In steady state, right? So if the bacteria has infinitely many time. Okay, so now what we could do with this knowledge is we could plug in this Poisson distribution in the binomial distribution that we have for the diffusion process, right? So somehow we want to couple these two processes. So what we could say is that the number of experiments or the number of trials that we do in our binomial experiment is a Poisson distributed random variable, where the Poisson distribution obviously comes from this chemical reaction network, right? So if we do this, we can use that, in this case, the random variable, which is the number of absorbed molecules, will also be Poisson distributed. Okay, so this is a known result. It can be shown. Some people have already shown it. So in the end, the number of molecules that we observe at the receiver, taking into account the randomness of molecule production at the bacteria cell, will be a Poisson distribution. And here, the mean of the Poisson distribution scales with both, basically. So the system parameters of the chemical reaction network and also the system parameters of the diffusion process. Okay? So, for example, for the mean value, we get this in approximation, and using this first term approximation, we get this term here, and for the variance, we get this term here. And again, we see all the system parameters reflected in these expressions, right? Okay. Okay, so then this is just to show that actually what we're doing is still sort of accurate. So if we do the stochastic simulation, as we discussed also in the first part, and evaluate the empirical probabilities, we see that we actually observe this Poisson distribution that we also derived theoretically. Okay, so okay, so in the end, that's almost all we want to do. The only thing that we're basically left with is what happens if the bacteria cell has not infinite time to produce molecules, right? So what if we have to stop the bacteria cell at some transient state and make it release molecules before it reaches the steady state? So for example, we want to have time-slotted transmission with some fixed symbol length t, and at some point in this time interval we want to make the bacteria release molecules, and now we want to determine, in terms of the received signal, in terms of its variance basically, what is the optimum point of time when we want to, when we should release basically the signaling molecules, right? So in order to answer this question, what we should have is a model, is a transient model for the probability distribution of produced signaling molecules at the bacteria cell, right? And it turns out that for a linear model, like the one that we have here, we can derive such a model in terms of the, by means of the method of generating functions. So I guess I won't go into detail here. Let's just say that we can transform the chemical master equation that we have into some other domain, which is the domain of the generating functions. And in this other domain, we obtain a partial differential equation, okay? So it's not longer discrete space, but we can transform it to continuous space, and the mapping is one-to-one. So there's no approximation involved, but we get basically this partial differential equation here. Which then again we can solve using the methods that Max presented basically. So we can apply separation of variables to obtain a series expansion of the solution to this differential equation in this form here, okay? And this would then eventually, if we evaluated this expression, this would give us the time-dependent probability of having some number of signaling molecules in the bacteria cells. Okay, so basically these figures, they just show how the basis function of this probability distribution would look like. So they would just be polynomials. So this is again back in discrete space, right? So they would be just polynomials of n, and they would oscillate at different frequencies. And if we looked at the steady state, so if we increased time t, we would see that if we weight these polynomials with their respective exponentials in time, they all of them would decay except for the steady state distribution, which would be basically the ultimately remaining one. Okay, and then finally, the last thing that we can do is we can plug in this distribution here that we obtained from the series expansion into expressions that we can derive for the mean number and the variance of observed signaling molecules. And what we end up would be, I mean, of course, an expression for the mean in terms of the absorption probability PA, and the mean of the number of signaling molecules, and also a similar expression basically for the variance. So, and from this equation we could finally observe the trade-off that we have in choosing the release time of the molecules, tau b, in terms of the coefficient of variation of the observed signal, right? So if we evaluated these expressions here for some set of parameters, we would, for example, observe these coefficients of variations. So having this analysis, we could, for example, choose some value tau b around this part here to minimize the coefficient of variation. Okay, so what you basically, or what we should take home from this last part of the tutorial is, depending basically on number on the type of question that we're interested in, different modeling techniques would be appropriate, and yeah, and that's it basically. So that's the main message, I guess. Yeah. And some examples are provided here. Yeah. Yeah, so I guess that concludes the third part. So.
Yeah, maybe just go on and for the concluding slides.
Yeah, I think you wanted to present them.
No, you can just go on. You're already in this concluding flow, and I think it's just 2 slides.
I think I conveyed I tried to convey the main message.
Yes.
So let's see what else we have. Okay, so a brief recap, I guess. So in the stochastic part, we have seen the largely diffusion models in the first part, and in the second part, we have seen the CME type models. We have also seen how they relate to each other, basically, and in a third part, in a third bullet point, which is not shown here, we have seen how to connect both of them in terms of the reaction diffusion master equation. Then in the second part, we learned some methods, basically how to model MC system in a deterministic scenario. So we have seen the reaction diffusion master equation in the end, and some solution techniques in terms of the transfer function, separation of variables, and so on. And finally, in the third part, we have seen some application examples. And yeah, and these are basically our take-home messages. So both, of course, both modeling techniques could be helpful for the analysis of MC systems. I mean, otherwise we probably wouldn't have presented them, right? And then it's pretty much what I said, or what I tried to say in the last part. Now it depends on the type of question that you're interested in, and of course also on the system dimension. So on the relative size of the system parameters, on which modeling technique is basically the appropriate one, right? So, okay, so I guess I don't know if we still have time for questions before lunch, or if we should go to lunch right now. What do you?
Well, first we can thank the speakers for presenting.